Hello, everyone. This is Spencer Snowling from Hatch. I'm glad that you could join us today for what is the last GPSX webinar for 2023. And I hope you're all doing well as we wind things down for the year. And so today's going to be probably a little bit of a shorter webinar than normal. I decided to cover off a number of things that have come up in tech support questions that have come our way over the past half a year or so, and a few things that I very often help people out with as part of support or training sessions that we do. And so today's going to be talking about troubleshooting basic simulation challenges with GPSX, things you're going to run into possibly from time to time that can be solved and will help you get over those hurdles. Okay, so as per usual, I'm going to ask you to type any questions that you have into the chat box or the Q&A panel. I'll check both places when we get to the end of the webinar. So I'll stick around after we do our little final presentation and answer as many questions as I can. All right, so over to the slide. To what I guess you would call sort of simulation issues. These are basic things that every once in a while will come up. And the ones that I'm going to talk about today are things that actually have nice, easy to solve problems, things that can be handled if you just know where to look, basically. So we're going to talk about problems with steady state convergence. We're going to talk about problems with reading in data, and then also some challenges around PID controller behavior in your model. So these are things that come up every once in a while, and we do answer these questions. So let's start with just a real sort of general introduction here. Most of the time, if you're sending in a GPSX question, you have a tech support question, you can do that by saying us your layout to support@hydromantis.com. And basically, we often see these three things come up over time. So, and I picked these ones because they are things that you can resolve on your own if you know which menu to do. And I'm hoping that this can become a good sort of support resource for you by coming to our YouTube channel in the future if you run into these. So as far as steady state convergence goes, as you probably know, it's quite common to run your simulations either only at steady state or run a dynamic simulation by doing steady state first. So that means that you have the steady state box checked on here. And when you hit the start button, you'll see this little crawl bar start at 0% and go over to the right and achieve 100%. And sometimes that's the answer that you were looking for, or sometimes you may also have some a value greater than 0 in the stop time over here, and then you're going to run a dynamic simulation from the beginning of the steady state answer. So that steady state solution predicts the behavior of the plant as if it's already been running for several weeks at a constant loading and operation. And so what it does is it solves for the condition of the model as if it has reached equilibrium. So that assumes that there's no changes happening at the plant either in terms of its operation or its loading, and therefore the answer you get out is sort of like typical operation. So the steady state solutions are a really common way to sort of do analysis of a wastewater treatment plant. And you can do a lot with just running steady state, to be honest. And they're very common when you're doing calibrations and general analyses, like a steady state sensitivity analysis, for example. So this is really what the visual representation of steady state is. It's a point where nothing is changing over time. And so this is an example where we're not running any dynamics at all. We just solved it for steady state, and then we ran it for 3 days, and you can see flat lines. Flat lines means it has reached steady state. Now, what you'll see here is if I run a dynamic simulation, it uses the steady state answer as the beginning of the dynamic simulation. So what you're seeing here is the flow going up and down over 3 days of diurnal flow. And these concentrations that are coming out the end of the plant, it uses the beginning of, at the end of the steady state solution as the beginning of the dynamic run. Okay. So the way we do that is by using the steady state solver, and that's a special solver that we have built in. That's a different solver to the regular dynamic one that we have. And it finds the concentrations throughout the plant that basically reduce the derivatives to 0. The derivatives are the way we do the mass balance across the plant. So those are being reduced to zero. We basically are taking every concentration at every connection point, and you'll see that those values go up and down over time while you're running dynamic simulations. But we use a special solver that finds the combination of all of those different parameters, and it basically does that until each one of the derivatives and the total sum of all of the derivatives gets down as low as possible, trying to get it to zero. It basically terminates, it reaches steady state, that's the 100% value, when it gets to a termination criteria, meaning the sum of all of the derivatives is now less than a particular threshold. And that is basically something like around 10, like an absolute sum of all of the derivatives in the model is a value of 10 by default, and I'll show you where to find that later. And that is kind of the value that we're shooting. Once it hits that, it stops, says it's good, all the mass balances are closed, and we're ready to go. So the solver has many parameters that make it a little bit more aggressive or a little bit more dampened down in order to sort of find good performance and get to the steady state solution as fast as possible. Now, for all your regular GPSX users, I'm sure you know that it reaches a steady state answer usually pretty quickly. We try to get it within 5 seconds, right? And but sometimes with more complex models, it might take longer. So what we can do is you might run into a point where you don't end up with 100% conversion. You might find that you run the simulation, it takes multiple stabs at it, and then it stops and says, this is the best I can do, right? So you got 19%. Now, at 19 is actually pretty low. Typically, if it fails to find steady state, it usually stops around 70%. And that's actually a pretty good answer, to be honest. It's not exactly wrong. It's very close. It might just be that our termination criteria is actually a little bit too aggressive. So, typical reasons for convergence failure. So one of them is very high concentrations in the clarifiers, and typically this happens when maybe you forgot to set the wastage rate, or it's not being turned, the wastage is not being turned on for some reason in your model. And so that means you basically have very large concentrations of solids at the bottom of the clarifier, and the solver's like having a little bit of problem getting to the exact answer there. You may find that the termination criteria is a little bit strict for the complexity of your layout. If you have a lot of objects on the drawing board, or if you're using a lot of biofilm objects, the biofilm objects have 6 times as many derivatives as a regular tank, because we're also solving for all the concentrations in all the layers of the biofilm. You might find that you have struggles with converging to steady state if you have overactive or poorly tuned PID controllers, particularly ones that are bouncing around a lot. That means the solver from one guess to the next is finding that things are changing and it's bouncing around a lot because the controllers are sort of bouncing back and forth. The oxidation ditch itself is sort of notoriously difficult to solve. And in general, if you have particularly large or complex layouts, it does take longer to solve to steady state. There's more mass balances to close, there's more degrees of freedom in the system itself, and so you may find that they take a little longer, or that they don't get all the way there, and so there's some things that you can do to help yourself along. So the way you can deal with this is to adjust the termination criteria and other parameters in the steady state solver settings menu. So if you right click on an open spot in the background of your drawing board and go to input parameters, steady state solver settings, it opens up this menu. And in here, I would recommend to start with by adjusting this number up here, which is 3 retries. It's basically the number of tries that it takes before it gives up. And if you increase this, it will take a number of shorter tries in succession to start, and then go into some longer attempts after that. So sometimes I find I put it up to 5 or 8 or something like that. That kind of helps sometimes if you have a particularly large one. It takes a couple of attempts to get at it. If you find that you have a very complex layout, if you have 20 or more things on your drawing board, or if you have biofilm models, this number might be unnecessarily low. It's an absolute value. So often I find if you get down to 100, then that is quite fine. Forcing it to get all the way from 100 down to 10 is usually overkill. So you may find you can actually open up the command window and take a look and see it moving all the way down from very large numbers all the way down to 10. And if it gets hung up around 40 or something, then by all means put this at a higher number so that it just winds things up and moves along. There's also one that you get if you go into the More button right here. And there's one more parameter of importance here called the damping factor on the final approach. This is a really good one too for, again, if you have very complex layouts and you got a lot of controllers in it. It's sort of basically, as you get down to those lower numbers, it sort of scales things a little bit, and it makes things a little bit, as it says, dampened down so that the dynamics don't change quite a bit from one iteration to the next. And then that often smooths things out enough that it can find its way to the answer. Okay, so that's in general for most of them. I did mention that the oxidation ditch is a particularly difficult one. It does have, it can be a particularly challenging model to solve. And the reason is, in this oxidation ditch, is we model it as 16 CSTRs in series, with the flow going all the way around and coming back. And of course, this flow around the ditch is very high compared to the flow through. Like this might be 20 or 50 or something times what the flow is through the ditch. So if you grab one of these cells that we're solving for, the concentrations in just one of these zones here, flow through is actually very, very high compared to the volume of it. It might be a residence time of something like a minute. So we find that a little bit challenging. And so we have actually, in the most recent version of GPSX, version 8.5, that I hope you're all enjoying using, in version 8.5, we added a new different kind of steady state solver for the oxidation ditch specifically. So if you go to the oxidation ditch operational menu and open this up and hit this More button here, you can get to a special menu specifically for this adapted steady state solver and turn that on. It will be off by default. If you turn that on, what it's going to do is it's going to make some assumptions about the ditch velocity, and it's going to actually make some better initial guesses for the concentrations that kind of go from wherever the aeration is happening downstream and around the tank. And generally, it works actually quite well. I recommend running a little bit of a dynamic simulation afterwards just to settle out any other remaining dynamics that would be there. I will mention, as I always like to do, to try to link to some other webinars that we've done in the past. If you are interested in learning more about our oxidation ditch model, we actually have a whole webinar on that we did a couple of years ago, modeling the oxidation ditch process. So if you go to our YouTube channel, youtube.com/Hydromantis, you can find that there. It won't mention the solver though, because that was actually made before we installed that new solver. Okay, so there's a few other objects that you'll find don't really do anything at steady state because they don't really have an actual steady state. So an SBR, sequencing batch reactor, is actually a perfect example of that. It is something that continuously is changing all the time. So the whole system doesn't really equilibrate to a steady state in like continuous steady state, because of course it's settling and then it's mixing again and then it's aerating and then it's decanting. So things are always changing. So there's a number of things like that. Our bath unit with the backwashing, the continuous flow sequencing reactor where the air goes on and off, the sand filter with its backwashing, basically anything that you put together using our custom timer, like intermittent aeration, those things don't really have what we would call a steady state, so to speak. So you may find that the steady state solver gets a bit confused about what it's supposed to be doing at that point. And so there's obviously, you don't need to worry about running it from steady state. In those cases, the units actually reach a sort of pseudo steady state where it has now kind of come into an equilibrium, and it's basically just repeating the same thing over and over again each cycle. That's kind of like the equilibrium that you're going for. But no matter what you're doing, in all the cases, the best way to check and make sure that you have fully converged model is to basically run a dynamic simulation after it has finished steady state, and then just let that run out for a few days, and then just see if the lines are flat. And if they are, then you'll know that you're at the right place. Okay, so I'm going to move on to talking about reading in data that you can use to either drive your simulations or to plot alongside model output. It's actually one of the most useful features of GPSX. We want to be able to either do this here, where you got a file input controller here, and the data is moving this thing up and down, and you're running a dynamic simulation where the flow changes over the day and over the week. And then also reading in some data and plotting the model alongside it to see how good your calibration is for it. So those things require us to make spreadsheets and get all that data in there. And sometimes you may run into a problem where it's just not reading that spreadsheet the way you wanted it to. So normally what you do is you take a spreadsheet and then you make a column for the time in the first left-hand column, and then as many other columns as you like that contain the data that you want to read in. So there's long time series of data being read in. And you need to get the correct cryptic variable names across the top. And that's generally the most challenging part, is just making sure you got all the names right. So one thing I'll mention is that you can hold your cursor over any place that you see the name of either an input variable or an output variable. So that's on any menu. Here it's showing that it's doing it on the file input controller that you get in the top left corner of your screen when you're running simulations. Actually, you can do it on graphs and output panels. Anything that has the name of a particular parameter, when you hold the cursor over it, you'll get to see this little blue tooltip that pops up. And there on the right-hand side is the cryptic variable name that you were looking for. That's the one that should go at the header at the top of your data file. And I will mention that how you set this all up and how you can get access to all this stuff is basically tutorial 6. So you either open up our tutorial guide in the help menu and take a look there, or you can actually watch the video on tutorial 6 at our YouTube channel. So the nice thing is you can either do that there and type it out, but even better is actually just right-click on that object, and then you can copy the cryptic variable name to the clipboard and then paste it into your spreadsheet. Even better than that is actually right-click on the tab up here at the top, and then it copies actually all of these, and then you can paste that into the spreadsheet all in one shot. So basically, if you're looking to put all of these together, there's a couple of nice, easy ways to get the names that you have, and it also will pick up the correct units for you here as well, and then paste those in too. Okay, so say you've got that all sorted out, and now I've got my data, and I've collected that probably from some other spreadsheets that you've got from the facility itself, reports or data historians that may spit out some data for you. And as typical in real life applications, there's sometimes when you have some missing data. So it might look something like this, where there's a few things, a couple of data points here and there that are blank. In this case, you need to do something about these things. If you leave them blank, then the spreadsheet will not be read in correctly. What you need to do is actually insert a question mark. It is a placeholder so that GPSX knows exactly how all of the data points fit together. And you can use that placeholder in the spot of anything that you don't know. So a blank spot that would be in your data sheet. So what the placeholder does is GPSX will hold on to the last value that it saw before it sees the question mark, and it keeps hanging on to it until it sees a new number again. So in this particular case over here, it's going to see this 34. It's going to hold on to 34 until it gets to this one down here. Excuse me, and switch to 24. So you might end up with a spreadsheet that looks like this. If you've compiled your spreadsheet in a way that is containing data that's been reported back to you at different frequencies or inconsistent frequencies, you might find that there are a lot of question marks that you have to put in. That's totally fine. It may look a little weird, but it is actually exactly the way that we want it to be. And it is actually a very powerful and flexible way for GPSX to handle data of different time steps. And it's actually a really useful thing for us to be able to have it all in one place and then be able to see everything in one spot. Okay, so one thing I would mention, I'd like to mention too, while I'm at it, is this is kind of a bit of an underutilized feature with respect to reading in your data. I want sort of highlight the fact that there can be a line that you can put into your data before the 0. This is STD, stands for steady state, meaning you can use these numbers. You can specify the numbers for the inputs that you want to be used at steady state. And it will use those ones first while solving the steady state model. And then it changes to the things that are to be used at time equals 0 and then onwards from there. This can actually be really good to sort of initialize your model really well. So it'll use these numbers in terms of what it does at steady state. Often what is probably the most correct way to represent this is probably the averages of the data that came right before this. This is the equilibrium of the plant based on the loading from the previous few weeks, the loading and operation. So that's kind of a good way to sort of take all those numbers that you had from the previous weeks put them in and take the averages of those, put those as your steady state, and then you're starting the simulation from a good place. Okay, and then one last thing I will mention when you're talking about using these spreadsheets and changing your data and editing a few things, make sure you close the spreadsheet before you start the simulation, before you hit the start button. If you have this open, the GPSX cannot read this file. It's, you know, just in the same way that you can't copy or rename or do things with your file if you have it open. GPSX also cannot read it as well. Okay, so that's a whole lot of discussion around the concepts of reading data in and getting data out of GPSX. And we have, of course, have a tutorial all about that, tutorial 6. And also we have an entire webinar on that we did a little while ago back at the beginning of the pandemic on getting data in and out of GPSX efficiently. We also did another webinar on advanced visualization methods that I believe also discusses getting data out of GPSX too. So that was just from a few months ago. Okay, onwards towards the last of the 3 demonstrations that I wanted to talk about today. And this one's a little bit the most complicated one. This is for PID controller behavior. So, and just to get the context, PID controllers are, you know, control loops that are included and put into the model to be able to control some aspect of that system, and you give control of a particular parameter to this loop. It is going to manipulate that value in order to get some other value to come to a particular set. So we're going to adjust the airflow in order to hit a dissolved oxygen set. Now we have a lot of these already implemented in many of the unit processes in GPSX. And many of them are already pre-configured and they're already tuned nicely, and they all are all nicely set up for you and ready to go. So the DO controller is an example of that. If you just select DO controller, which is also the default, having that turned on, and you set these set points, it will adjust the amount of air that is required to meet those, and then you can plot the air and see how much that was. Some other controllers that are built into our menus are there for you to use. So they're built into the controller. Sorry, pardon me, they're built into the pump connection point, but we don't know exactly ahead of time what thing it is that you would like to control. So in those cases, you have to open up the menu, specify the thing that it is that you're trying to control, and then you have to specify some details around that, and also tune it and various other things. So, for example, an MLSS controller would need to be set up with the appropriate names and also tuned properly. And in addition to that, we also have this generic PID object that goes on the drawing board, and then you can set up any PID controller that you like, any manipulated variable trying to control any control variable. And this one is sort of the most generic, so it needs the most setup. So after you've got that on the drawing board and you've put in all the information, the challenge might be that you find that it does not meet the set point, even after you've got it all set up and everything seems to be running okay. And there's a number of different reasons why that might happen. So one of them is that you have not actually specified the correct control variable name. Again, it has to be the cryptic variable, so sometimes that's not extremely obvious what that should be. Sometimes the controller sampling interval is too long or inappropriate for the type of controller that you are using. It might be just tuned badly, so it can't get to the set point because it's way over aggressive or not aggressive enough. And also you might have some minimum and maximum bounds that are there, and that might not be set quite the way that you want it to. So I'm going to touch on each of these sort of individually here. So basically, this is probably the most sort of a tricky thing to get right, which is finding the correct cryptic variable name for the manipulated variable and for the control variable. So in things like the DO controller that's already built into the object, we've already done that work for you. So what I'm showing you here is the one where you're putting down an object on the drawing board, and you have to do the work of finding the correct variable names. So as you can see here, just like any other place, if I put my cursor over the menu item, so this is the WAS pump flow, we're going to make an MLSS controller in this case, right? We're going to change the amount of wastage to try and hit a mixed liquor set. So in this case, if I hold my cursor there, then this little tooltip pops up, and this right-hand side here is the the cryptic variable name. Now, we need to split it actually into two different things that we enter here. One of them is the manipulated variable name itself without the label, and then the label. So you can see over here, this is actually the label name. It always appears to the left of the variable itself. That is actually the value or the name that you entered in when you built the layout. You gave this connection point that name. So that has what goes into the label part, and then the remaining part here, QCon, is the other part that goes actually into this other section. So for the generic PID object, you break that up and you put it that way, and then it puts those two things together and knows which thing to do and gives everything its own unique variable name so that you can have multiple PID controllers on your drawing board at the same time. Okay, that's first step, get the manipulated variable down right. Now we need to specify the control variable. This is the thing that we are trying to control and push to its correct set. So that is the same deal. Basically, you open up the menu, find the thing that it is you're trying to control, hold your cursor over it and get that cryptic variable name, or as I've shown you on the earlier slide, right-click on it and you can just copy it and then come and paste it here. The second thing you need to think about is the sampling time. How frequently does this controller take an action? And so in that case, this is showing our default value is once every 5 minutes, the controller will increase or decrease the DO or the wastage or whatever it is. So in this case, it's going to adjust the amount of sludge waste that we're doing, right? It's going to change the flow rate. So is that an appropriate time? Well, it all depends on what you're trying to model. We picked 5 minutes in the sense that it will act fairly frequently and you'll see something happening, but whether or not that's appropriate for what's going on at your facility, you'll have to figure that out. But it is, if you were to enter in a number here that was actually too large, like say you said once every hour or once every day, maybe that's not frequent enough for your controller to actually keep up with the changes that are happening in the facility. So just make sure this number is not too small. Sorry, pardon me. Make sure it is not too big and make sure it is small enough. Okay, the second thing is these three parameters here are your PID controller tuning. So the proportional gain, the integral time, and the derivative time. That is the P, I, and D sections here of your PID controller. Now, these, the time ones are in units of days, but the gain is in the units, the default SI or metric units that we use in GPSX. So if you take a look at them by going to the meters cubed version of your whatever flow rate you're working in, a good starting point is to just basically take for the default setting that we have, the manipulated variable and divide it by the control variable, and that will give you an approximate order of magnitude to put your gain at. You will then probably need to adjust it from there, but that's always kind of the way I start. And basically, in this case that we're dealing with, the manipulated variable is something like 50 meters cubed, and the mixed liquor is something like 2,000. So therefore, it is going to be sort of tens divided by thousands, so therefore it's 0.01. That's a good starting place to kind of get it there. And if you want to make it more aggressive, then you go up or down from that point. Now, this is the other important parameter to be able to deal with. And this is a difficult parameter to describe on a very short menu here. Basically, it's asking what is the controller effect on the control variable? So when I change the manipulated value, what happens to the control? Do they act in the same direction or do they act in opposite directions? So for our mixed liquor controller example that we have today, if I change the manipulated variable, that's the wastage. If I increase the wastage, then it causes the control variable, the mixed liquor, to go down. So that means these act in opposite directions, which means this should be off. If it was a DO controller, for example, increasing the airflow would increase the DO, then we would want this on. So basically all this really does is it takes our PID control equation and either it puts a negative sign in front of it or it doesn't. That's what's happening in the background. But basically we just need to know what is the direction and you either have this on or off accordingly. So just think through it, a change in your manipulated variable, what's going to happen to your control. So if you have this the wrong way, for sure your controller will not work. Okay, lastly, there are minimum and maximum values for your manipulated variable. That is always a good idea. Of course, we want the model to behave in a sort of realistic way. So you can only pump so much, for example. And so these minimum and maximum values are found, depends on which menu you're dealing in, but here you can see they're at the bottom of the first menu. And these are just basically taking this at whatever is the minimum and maximum value. And again, it's going to be for this generic PID object in the default metric units. So in this case here, it's at 0 and 500 meters cubed per day is the maximums with sludge wastage that we can do. Now, I will again mention that we have covered how to set up PID controllers and how to do advanced process control using combinations of controllers and even custom coding in past webinars. In fact, just earlier this summer, we did one on implementing custom flow control algorithms in GPSX. And that covered off using these types of controllers, plus also writing your own type of custom controllers. This older one that I did 3 years ago is also a really good one. It kind of covers some of the same material, but both of those cover how to do all of this in a way. So if you're interested in doing advanced process control, I recommend checking those out. Okay, I want to do at least one demo. It wouldn't feel like a real GPSX webinar if I didn't run something live in front of you accordingly. So this is a very simple plant. This is adapted actually from the tutorial 6 layout that you may find if you have gone through our tutorials. I dropped this waste controller on here, wastage controller. This is going to control the waste and it's going to control the mixed liquor here. I suppose I actually should have called that a mixed liquor controller. It's doing it by adjusting the wastage, right? And if I go in here, some of those screenshots that I was showing you on the slideshows came from me setting this up here. And you can see there's the manipulated variable that I set up. We're going to have our mixed liquor hang in here around 2,500 milligrams per liter. I've set a minimum and a maximum. And if I go in here as well, I've made, there's specifying the control variable. And I've made a couple of small changes to the tuning as we had discussed earlier, right? So, and I've left the sampling interval at 5 minutes. So that is telling us we're going to control this mixed liquor using this tuning, and we're doing it via adjustment of this particular parameter. All right, so over to simulation mode, and I'm just going to really quickly describe what I've got on the graphs here so you'll know what you're looking at. The upper graph is basically going to show you the set point and then the actual mixed liquor, and we'll see whether we're doing a good job or not. And then down here in green is going to be the wastage flow that was required to meet that set point. And then in red will be the minimum and maximum bounds on that. And then so over here, just thought I'd mention that I'm going to be running a 2-day simulation with an influent flow that goes up and down in a regular diurnal pattern. So you can see that. Okay, so here is our default situation for the investigation today, showing that our mixed liquor controller is doing the job. It shows that it's wasting how much here? 52 meters cubed per day. And it's doing that almost 53 pretty consistently, pretty flat in order to meet that mixed liquor. Now, this is a mixed liquor controller, so it doesn't, that's not something that changes very, very quickly like DO does. So we would expect to see relatively flat kind of behavior. Okay, so what happens if I make some changes here? So I started this off in a good place, but I wanted to show you places where maybe it wouldn't behave quite that nicely. So right here, you can see there's some tuning here that's gained. Like what if I had actually left the gain at the default of 1? And so I'm going to rerun that again. And first of all, you can see down here, that other issue that I mentioned earlier, if you have over-aggressive controllers, it makes it harder to solve for steady state. And in that case, it took 3 tries at getting it right before it got there. Okay, you can see now that, of course, it's still hanging around. And in fact, it's kind of overshooting a little bit here. You can see that the wastage is just kind of going up and down wildly here, because we now have a very aggressive controller. So it took a little bit of a dip below the line here. I mean, you can hardly see it almost. And then it went way up here. Now this came down and so on. So this is a very overly aggressive controller. And if we were to, be even worse, obviously that will get, much worse behavior as well. Okay. So what you don't want to have is your controller do this, which is waste a lot, then waste nothing, waste a lot, and back and forth like that. So obviously, that's a case where you would want to revisit your tuning. Okay, I'm going to put that back. I'm also going to talk about let's go back to a good simulation. And then the integral time, which is the other one that is typically something you want to play around with. It is, of course, the other way around. Reducing the value makes it more aggressive. So I'm going to do that. And here you can see the kind of behavior where we're not, it's hanging around the set point properly, but, you wouldn't want to shut off your pump altogether for a day or have it maxed out for a day. This is also a good point to see here that the controller came up here aggressively and then it hit that max, right? So you can see that it can't really do the job that it wanted to do up here. Eventually it came down when the loading changed anyway. So, but just to point out that if you see this kind of fluctuating up and down behavior on your manipulated variable, then that means that probably your controller is not quite where you want it to be, even though it's actually meeting the set point. So now I'm going to flip to another scenario. Let's go to the higher loading scenario. This is one that I wanted to specifically point out where this is one where the max comes into play. The max limit on the manipulated variable comes into play, and you can't actually meet the set. So now you notice I basically had doubled the influent flow in this scenario. And so now you can see it's now wasting quite a bit more than it was before. So it's now 81 meters cubed per day instead of the 52 earlier. And that's what's required to keep it at the the mixed liquor set point. And then now, what if I wanted a set point down a little bit lower? Like let's set this to 1500. Like say you're having some clarifier issues and you want to run a little bit lower mixed liquor. So now we're in a situation where we're not meeting the set point anymore. We're above the set point, and that is because down here we're maxed out with 100 meters cubed per day. So therefore we can't get all the way down to our set point. All right, so basically those mins and maxes and your tuning of your controller, those can all be things that can go awry and also not allow you to sort of achieve the performance that you want. And but in the end, adjustment of those parameters will help you out. Okay, lastly, we can now talk about a couple of other things that come up every once in a while that I help out people with and as part of tech support. Some people have asked me in the past about this particular message that you can get when using GPSX. If you're making adjustments to various types of graphs on the right-hand side in simulation mode, basically this says more than one variable assigned to the bar chart. So in this case, what this means is you had probably in the past made a graph that had multiple parameters on it. Like say you were plotting effluent TSS and BOD on the same graph, and then you flipped it over to a bar chart because you maybe for whatever reason you wanted to see that as a bar chart. If you have multiple parameters and you flip it to a bar chart, you'll see this message. What it means is you cannot show two different things on a bar chart at the same time. And the solution is pretty straightforward. Go back to making it an XY graph again, and then split them up. Just drag one of them over to a blank spot, make it its own separate graph, and then you can switch both of those to bar charts, and then you'll be ready to go. And another one, just because the other day, my colleague Jake and I were just helping out a client with this exact issue. We were plotting this graph, but nothing's happening. Where we see the red line, where's the black line? It's not showing. And the reason is because in this case, it was just an issue of what scale were you showing on your graph on the left-hand side there. And what you can do is a nice, really quick and easy way to see if something is not showing because it's off the top of the graph is to just left click on the graph. So use your mouse, just click somewhere, and you'll get this little box popped up. And you can see here that it's showing you the value of all of the variables that are being plotted on this graph. And you can see that this 2000 is off the top of the scale there. So that's fairly straightforward. The reason is because in this particular case, the auto scale was not selected. And sometimes, quite frequently, you don't necessarily want to auto scale, but you will notice that you, of course, have the opportunity to set the maximum graph that you like, or graph scale that you like. And if you put that little lock, if you click on the lock right here and lock it, then it's going to put these two things together on the same scale. And that's one nice way to kind of keep everything in the same order of magnitude so you can see what's happening. All right, so just to keep an eye that if something's missing, it's probably gone off the top of the graph. Just click on it once and you'll be able to see what the value is. Okay, so since we've been talking a lot about tech support, I thought I'd make one final message here about this sort of, I guess I can't really call it new because we've been doing it for 6 months now, but our tech support ticketing system. And so we implemented this back in, I think we started in June. So we've been going at it for about 6 months and we kind of worked out all the kinks now. So it's called Jira Service Desk. And it is from a company called Atlassian. So you might see emails from either of these names. And it is a ticketing system where you can log in, you can specify all the questions that you want, and then you can actually attach your GPSX layouts. And this has been advantageous for us. We do have some clients now and again who have some difficulty emailing us their GPSX layouts because their email system might not like sending attachments. And so this is a nice way. You can just upload the attachments directly. We can get them. You can have them. We can pass them back and forth without having to go through email. It's a nice way to do that. So if you send us a question and we want to set it up for you in the ticketing system, you'll receive an invitation to set up your account, give it a password, and then you're good to go. So now, that's one thing I should mention is the old way of doing things also still works and still applies. If you want, you can send us an email to support@hydromantis.com. So typically these days, if you send us an email to the old one, we'll set it up in this ticketing system for you. But if you have an account, you can just jump straight in and just create a new ticket there if you like. So it's been helpful for us as we have more people dealing with providing support to our clients and also being able to send the layouts back and forth. This helps a lot. So this is what it looks like. You will see a page with something like this with the question that you have asked to us. And then anything that we do back and forth will happen here. You can also respond to the emails that you get from this system. And it will update here as well, as long as you don't change the subject line. Anything you send back to us by email will also get posted here as well. Okay, so final thoughts. Basically, this has been a webinar designed to help you with challenges that users do run into from time to time. And these are all ones that basically can be easily addressed if you sort of know where to look. The steady state solver settings, as I pointed out, can really help you with that convergence. The data files are really flexible, but there is some kind of formatting. And in particular, any place where you have a missing data point, put a question mark. And then the PID controllers. Some of them are set up nicely already for you, like the DO controllers. But if you're doing a generic one, or you're setting up something that requires you to specify the control variable, then you're going to have to do some setup and tuning of that control loop. However, as always, if you have any questions, please feel free to email us or send us a ticket through the ticketing system if you have any questions and if you need any assistance.